Steve. So I wrote on the board the category that this talk is about. I liked a question Eva asked a few weeks ago of one speaker. What was the category of their talk? I think it was the question. But the question or the category is, what is the relationship between vacuum entanglement and quantum spacetime? As has been discussed many, many times here so far. There are a lot of indications that there is a deep relationship, and I won't go into what all those are, but I'll be talking about one of them. I want to start with just the idea that there are two equivalence principles, in a sense, that that lie perhaps at the root of this relationship. One's the usual space-time equivalence principle, which geometrically we can state by the fact that all spacetimes are flat in a sufficiently small neighborhood of any point. So that we can transform away gravity, and it's just a statement of the nature of space-time geometry. But there's also a quantum field theory equivalence principle, I think, which we could say that all states are vacuum in a small neighborhood, in the sense that, the short distance structure of states in quantum field theory, at least so far from anything I've seen, we don't mess with that. There's kind of a universal short distance scaling limit. And these two are very intimately tied together, and what I'll talk about today is trying to use that fact to understand better this relationship. So I'll begin by just recalling the old idea that that we could derive the Einstein equation from black hole thermodynamics. And I'm just recalling it because it will form the sort of spiritual basis of what I'll be doing today, which is a different way of getting the Einstein equation out of entanglement. And so the idea there was just that if we had a black hole horizon, we know that black hole horizons satisfy laws of thermodynamics, and in particular, at a given point on the horizon, we have a light cone. The horizon is ruled by null geodesics. When matter flows into a black hole, the horizon area increases, and it does so in a way that's consistent with the laws of thermodynamics. And the puzzle is sort of, why did general relativity have the structure that would make a black hole behave thermodynamically? And so I think the answer to that is to be found in these equivalence principles. To just say, look, forget that you had a black hole. Just pick this point, let's say, and look at a small neighborhood of it. That could have been a point in any space-time anywhere, whether there was a black hole or not. And blow that up and just analyze that process from the viewpoint of using these equivalence principles. So then we could set up, here we have a slice of the horizon, and it has a certain area, and that evolves in time. But instead, we could just take a little piece of that slice and put that through any point in space-time in a small neighborhood. So this whole thing now is one of these small neighborhoods I'm talking about. Look at the boundary of the past of that. We get a little section of a causal horizon. And we can analyze the change in area along that horizon as energy flows through it. Now, what do I mean by energy? Let me draw the picture again, just cutting across it in Minkowski space. So this point will represent this entire little section of area. And I'm going to use the fact that the space-time is approximately flat to set up a local Rindler coordinate system and a Rindler horizon. And here will be the bifurcation surface of it. So I have a flow of a boost killing vector here. And because all states are vacuum at short distances, the quantum field looks approximately like the vacuum, just slightly different from it here. And that means that, as we know, that it's in a thermal state. You have a thermal vacuum, which means that the density matrix restricted to this Rindler wedge goes like e to the minus h, let's call it c over t. C is the boost killing vector. And that looks like a thermal density matrix, and the temperature is just h bar over 2 pi. It's got dimensions of action instead of energy because the boost generator is a generator of hyperbolic angle transformations rather than some proper time translation. So we can think of the quantum fields at short distances around any point as being a thermal state, or almost a slight perturbation of a thermal state. That thermal state has entropy. That's a mixed state. It's got, in fact, a huge amount of entropy. It would be infinite in quantum field theory without a UV cutoff. But we could imagine, and we know because black hole entropy is finite, that there is some kind of a UV cutoff related to gravity, presumably. So the entanglement entropy has a leading order large piece, a UV contribution that comes from the horizon. And we'll
Sorry, why do we need a UV cutoff for that statement? Because it's canceled by the Casimir energy, right?
What Casimir energy? This is entropy.
The temperature. You said that the energy density.
I'm just saying the entropy would be infinite in continuum QFT.
Yeah.
So it's going to scale with the area. This will be some constant with dimensions of 1 over length squared. And suppose we just assume, because we know it from black hole physics, that this turns out to be finite. So there's some UV cutoff that makes it finite. So we're going to say that alpha is less than, is finite. And most importantly, alpha is state independent. It's just a universal property of the vacuum. So state independent. Okay, so we have a thermal state with some entropy.
Sorry, just so I understand, this is in the context with non-zero G Newton. I mean, you have gravity turned on, right, to say these things? Or?
Right, otherwise this would turn out to be infinite.
Infinite, right. Okay.
So looking at this now, a slight perturbation of this thermal state would involve something besides vacuum. And if any boost energy flows from this system we're talking about across this horizon, from all the observables inside this region, once that has flowed into the near horizon region, basically can't distinguish the form that the energy has taken. This is this old argument I gave 20 years ago or something. So we can think of that as heat going into this reservoir. And the heat would just be the change in boost energy, which is the integral, the flux of it over the horizon, let's call that h, would be the energy momentum tensor contracted with the boost killing vector, so that's the current of boost energy integrated over the horizon. That's the boost energy flux. Now, in thermodynamics, heat flow is related to entropy change by the Clausius relation, which says that the entropy change is the heat flow into the system over the temperature. And basically identifying this entropy change with the change of this entanglement entropy and the heat flux with this integral of the energy momentum tensor and the temperature with this temperature of the vacuum, one can show that that implies Einstein's equation holds. If it's true for all points here in space-time with all possible orientations of the null surface, then a consequence of that is that GAB contracted with any null vector KA, KB is equal to, let's see, the coefficient is, let's do it this way, 8 pi G Newton TAB KA KB, where G Newton is 1 over 4 H bar alpha. So if this is true for all null vectors K, then up to something proportional to the metric, we have Einstein's equation. And then the Bianchi identity tells us that that we actually have Einstein's equation with some undetermined cosmological constant.
So where in that step does GAB appear? That was very quick.
Pardon?
How does GAB appear
Oh.
in that derivation?
The ds means the amount by which the area of this changes. And so asserting this equation is true is saying anytime you have flux of the energy momentum tensor or the boost energy current, there must be a change of area. So that tells you that the null geodesic propagation cannot be independent of the flux of energy. It must be dynamical. And we can quantify the amount of area change by the amount of Ricci tensor there. There's an equation that relates the area change to the curvature tensor contracted with the null vector tangent to these curves. And that brings in the Einstein tensor.
Does this somehow rule out R-squared gravity?
It doesn't rule it out, but that would correspond to correction terms to what the entanglement is, subleading terms.
Does it rule out no gravity?
I think it does rule out no gravity if the entropy is finite. And this interpretation is right. It's kind of interesting that, so in the case where the entropy is actually infinite, alpha is infinite, G Newton is 0, there's no gravity. The more entanglement there is, the smaller G Newton is, so the more sort of rigid space-time is. Entanglement is a measure of, this vacuum entanglement is a measure of, or creates the rigidity somehow of space-time. I'm not claiming this is a logically clear argument. I'm just, it's interesting. The pieces kind of make sense. It's sort of fuzzy. What I'll tell you about today is a much sharper version of this, which is inspired by recent work in ADS-CFT, although it won't actually make use of the holography, but it's inspired by that.
What do you do if there's no matter? How do you get the Einstein equation without matter? Would you use TAB gravity?
You'd have 0, and then you'd just find the space-time is Ricci flat.
Isn't there some subtlety about the direction of flow? Because so you have to get the area to always increase, right?
Yeah. I don't think there's a subtlety. There is. It's important that this endpoint, I don't want to spend too much time on this because I think what I'm going to present today is a real improvement over this. But we have to think about this process as a relaxation to equilibrium. So the point here should be the analog of an equilibrium point. And that means the area should be instantaneously not changing as these null geodesics meet the surface. So that's a kind of final boundary condition, that the expansion of the congruence vanishes at that point. I think that probably is what underlies what you're asking.
But Ted, I just wanted to point out that there's something written on the board that is actually not true in quantum field theory, namely that all states in a small neighborhood are close to the vacuum. Most of the states in a small neighborhood in quantum field theory are not close to the vacuum. And I don't think that that takes away from this derivation at all. It just says something that we know on other grounds, namely that most of the states that quantum field theory attributes to that region are not really there.
Oh, yeah. What I mean is the states that we ever need to deal with, apparently.
Right.
Yeah, at least in semi-classical settings.
I think there's an order of limits issue here. If you have a
Absolutely.
particular scale, of course, most of the states defined at that scale are excited relative to the vacuum. But if you take any particular state in d greater than 2 dimensions that has excitations at a given scale and zoom way in, it looks like the vacuum.
Yeah.
Right. A sort of similar question is the equivalence principle for the field theory the same as the small scale structure, the Hadamard structure of the correlators?
Yeah, that's what I was thinking of.
I didn't quite get, have you just derived classical or quantum?
I think it's classical at this point.
So why do you need this?
It's like thermodynamic. What?
Why do you need this quantum argument?
Well, because otherwise I would have no reason to think of the vacuum as a thermal state to assign entropy to the wedge and to identify boost energy flux as heat. The whole idea, all of those ideas only become sensible once I've looked at the vacuum as a thermal state in the wedge.
You're deriving a classical result by sneaking H bar in first, right? Is that a problem?
Well, I didn't sneak it in. It came in through this temperature.
Yeah.
But I mean,
No, it shows you that Newton's constant has something to do with h bar at the deep level in this approach.
Right.
But let's not hesitate too much on this because, like I said, I think I'm going to offer something that's an improvement on this.
should let you go on. Well,
Okay, I'm just follow up on Andy's question. Like, can we actually like take no matter case and just consider gravitational waves, like DAB being sourced by gravitational waves?
I don't think it makes sense to include gravitational waves in TAB here because I'm zoomed in on such a small neighborhood that I can't identify the energy in the gravitational wave. You know, that only can be seen once you're in a region larger than the wavelength of the gravitational wave, which is also a measure of the radius of curvature. So, but I'm specifically focusing on a region that's small compared to the radius of curvature. So I don't think the gravitational wave energy enters on this side of the equation. I think it enters on this.
somehow magically the nonlinear terms come out. I'm not seeing how
Yeah.
they do.
Okay, so that was just to maybe show you what I'd like to improve on, but I do think it's suggestive enough to be worth improving on. Okay, so recently, related but quite different ideas have come up in the context of holography, I think, but I'm not sure. This was originated by Van Ramsdonk, McDermott, and Lashkari, which is to use the following concept. So another way of getting the Einstein equation related to entanglement and similar ideas is to look at the CFT and a ball-shaped region. Conformal field theory in a ball-shaped region, the vacuum is exactly thermal with respect to not the boost generator, but the conformal boost generator that preserves the ball. And so we have the fact that, say, rho in the ball is Z inverse e to the minus h, I'll call it zeta over t. It's the same t, but now zeta is the conformal boost killing vector. Now, since this is of the form of a thermal state, the standard fact that the free energy is minimized in that state is true. So if we were to write the free energy as E minus Ts, and then 0 equals the variation of the free energy. If we're talking about varying to a state near the vacuum, this would be the variation of energy minus T variation of S.
So your rho ball is a reduced density matrix inside the ball? It's the reduced density matrix
Yes.
that you traced over everything else.
Exactly. Thanks. And what energy are we talking about here? Well, it's the energy that this Hamiltonian defines. That's the conformal boost energy. And that's usually written in terms of this so-called modular Hamiltonian K. So that's the variation of the expectation value of K, I'll call it K sub zeta minus T delta S. Okay, so that's one starting point. That's just a fact about quantum field theory. On the other hand, from holography, the entropy inside here is related to the area of a minimal surface that goes down into the bulk. Minimal surface by the Ryu-Takanagi formula. So this formula can be translated into a statement that links the change in the area of the minimal surface to the variation of the boost energy of the conformal boost energy. That conformal boost energy can also be written as an integral like this over the ball, where replacing C by this conformal boost killing vector. And that just involves the energy momentum tensor in the CFT up here. But according to the ADS CFT dictionary, that stress tensor is related to asymptotic form of the metric in the bulk. And that way, this part of the equation can also be tied to the metric inside the bulk. So this equation becomes a relationship between the area of this minimal surface and the metric in the bulk. And these guys showed that that actually implies the linearized Einstein equation if you apply it to all possible balls on all possible surfaces in the CFT. Yes?
No, but when you assume that entanglement entropy is minimal surface, you kind of assume there are no higher derivative corrections.
Right.
So you kind of assume that there is an Einstein gravity, and then you derive Einstein gravity.
No, well, you're assuming a leading order form in a sort of derivative expansion of the entropy.
Yeah, I think this derivative shows that it's equivalent to assume the Einstein action or to assume the Ruta-Kanai formula for the entropy.
Yeah, right. Yeah, I think, but in any case, this is a connection is set up.
Could you draw that Killing back? I'm confused about what this zeta is. What?
I'll talk about it in detail a little bit later.
Okay.
I'll write it down what it is.
Right.
Okay, so the statement is that this is this implies if we, well, let's say plus Ryuta-Kiyanagi formula and ADS CFT dictionary. This implies the linearized Einstein in the bulk.
Yeah, you usually don't need you don't need anything else from the ADS CFT dictionary. Turns out this
from the
connection
follow-up.
with the stress tensor and the asymptotic metric also follows from Ryuta-Kiyanagi.
Oh, really?
Yeah, if I apply Ryuta-Kiyanagi to little infinitesimal balls, then that formula tells me that the stress tensor is related to this little area of the little ball, and that you can relate to the asymptotic metric. So.
Oh, that's great. Okay. Okay, so you can see there's some relation between these ideas, but they look quite different. Now, the whole point really of this talk is to combine these two ideas. So instead of using holography, but using the concept of the conformal killing vector giving you a handle on entanglement in a ball, I want to apply this idea in space-time locally, still invoking the same equivalence principles, but now not on an evolving causal horizon, but just in a region. And the region will be a causal diamond. So now I need to do a little bit of geometry, because this is the domain that we'll be applying this to. So I want to pick any point in space-time, pick any time-like unit vector there. And then orthogonal to that is a hyperplane. And we shoot out geodesics in all directions and generate a geodesic ball of a fixed radius. So this is a geodesic ball of radius L. And I'm going to be taking L to be small compared to various things, and I'll say later exactly not how small it should be. So we have a geodesic ball. Now by construction, the extrinsic curvature vanishes at this point because it's a totally geodesic surface at that point. So KAB equals 0 at P. Let's call that point P. And we can set up a Riemann normal coordinate system here and calculate how much the area of the boundary of the ball and the volume of the ball depend on the curvature here. Now I want to make L small, much smaller than the radius of curvature of the space-time here. So take L much smaller than, I'll call it lambda curvature. It'll also be smaller than other things later. This will allow me to do a derivative expansion and only include, well, to treat the curvature as constant over the entire ball. So then using a Riemann normal coordinate system, I can calculate the area and volume, rather the variations that depend on the curvature, and I get the following formulas. minus L to the d plus 1, area of a unit d minus 2 sphere over 3d squared minus 1 times the Einstein tensor.
This is a change in the volume when you do what? When you vary the metric in a neighborhood of P?
Exactly. And the variation you're picking up on is just the value of the Einstein tensor at the center, and you're ignoring derivatives of the Einstein tensor or of the Riemann tensor across that region. So it's just Riemann tensor evaluated right here is what comes in. Because, as you know, the Riemann normal coordinate system describes the metric in this neighborhood as flat up to the second order in the coordinates, and the second order term is just controlled by the Riemann tensor at the center. And then we also have the area variation, which is also negative, and it's 3d minus 1 d naught naught. Right. So just to pause, it's interesting just classically to notice that you can therefore express the Einstein equation as the statement that the area is negative, is a little bit negative compared to what it would have been in flat space for a ball of the same radius, by an amount which is governed by the energy density. Because if we impose the Einstein equation, this just becomes proportional to T naught naught. Naught naught just means the contraction twice with this time-like unit vector. So the Einstein equation, and then if we vary the point and vary this unit vector, and we get all possible components of the Einstein equation, and so this is really equivalent to the statement of the Einstein equation. And therefore, I finally understand what I read in the Feynman lectures when I was an undergraduate. He describes general relativity, and he says the Einstein equation is the statement that that there's a length excess of any ball that's proportional to the amount of mass inside the ball. There's a formula in there, and you can derive that formula from this. He didn't explain carefully that the ball had to be a geodesic ball, but that's what it is.
So in the first argument, you only got that you couldn't get the cosmological constant. Does that happen here too? I don't see.
Well, I haven't made a derivation yet. I'm just saying if you had the Einstein equation. What I will eventually do is have trouble getting the cosmological constant.
Good.
And I have some ideas about it, but I'm really quite confused, and that's why I said I'd like somebody to explain to me how to get it. It's interesting why I have trouble, and I have ideas that look promising for how to get it right, but I'm still confused about it. Okay. Right. I also just want to mention for the relativists, really, that this is also the same as the usual constraint equation. The constraint equation says, extrinsic curvature squared plus three-dimensional Ricci scalar goes like energy density. Here, at this point, the extrinsic curvature vanishes by construction for this surface. So we just get that the Ricci scalar of space is proportional to energy density. But you can easily show that when the extrinsic curvature vanishes, the Ricci scalar is also, it's 1/2 G naught naught. So this is just, again, a familiar statement of coming from the Einstein equations, if you know about that.
So, sorry, I have a dumb question, but I'm trying to connect this to, suppose you considered the expansion of space as a generated by some stress energy source, say like in cosmology. Then if you increase the stress energy, the space expands more as a result of that. So you have a Friedman equation instead of the equation that you wrote there involving the space.
Well, you see, this was constructed as a specific kind of surface, a geodesic ball. So you're...
I'm just trying to get the right intuition.
If I can help her get some intuition. So, as you said, the key thing here is that your surface has no extrinsic curvature, so it's like it's instantaneously time reversal symmetric. So think about your cosmology at the moment of its maximum expansion if it's a recollapsing. That would be the analogy.
But you don't have to take that moment. At any point in an expanding universe...
Sorry, so if you add matter to that, it does make it crunch more, I guess is what you're saying.
I haven't thought through it, but it must work out in that context.
Yeah, it does. Okay. That's the intuition that adding matter makes it actually shrink.
Or increasing the matter energy density makes it smaller.
I think this is not supposed to be a dynamical. This is like a.
At this point, it's a static discussion.
Comparison with flat spins.
Right. Okay. So that's one little piece of ingredient we need. The other one is about the conformal killing vector that Andy asked about. So I need to explain exactly what that is. So let's consider any conformally flat space-time. And let's write the metric as a conformal factor, therefore, times Minkowski, and I'll do it in double null coordinates. Then any transformation that sends u to a function of u and v to a function of v is a conformal transformation of this piece of the metric, but not of this piece in general. But we can add the requirement. So what I'm saying is I could put a of u d by du plus b of v d by dv as a candidate conformal killing vector, and it would have been a killing vector of this piece, but it's not for this piece. But if we also require that the conformal factor that pops out from here when you act with this vector field on this is the same as the one you get from acting on this, that tells you that the function b must be equal to the function a. So conformal implies b of v equals a of v. So there's really just one function. And that's actually not enough. It must be a function of the form a plus bv plus cv squared. So this is the only choice. This generates an SL2R algebra of conformal killing vectors of Minkowski space. But they're still not conformal killing vectors of my diamond. So the thing I'm going to be interested in is the causal diamond generated by this surface. In a curved space, we could define it as the domain of dependence of this ball that I generated. It will look something like that. In practice, for what I'm doing, I actually only need it in flat space because I'm considering a first-order variation.
Sorry, the conformal group of Minkowski space is bigger than this, right?
Yeah, this is the part, I picked a special form, and this is just the part that that's spherically symmetric in this particular coordinate system. So I'm adapting it to that because I'm going to be, this cone has a preferred time-like direction, and I want to preserve, ultimately what I want to do is preserve this whole cone region, double cone. To do that is, so to preserve the diamond, that requires that A at plus and minus L equals 0. So the diamond is at, in these coordinates, this is t equals 0, u equals t minus r, v equals t plus r. So at r equals 0, they're just equal to t, and this is u equals minus L, u equals plus L. So to preserve this diamond, that has to be true. And this ends up selecting that there's no b term, and that a is really just, and that these two are equal. So a of b has to be a constant times 1, actually opposite, 1 minus v squared over L squared. So we get a unique conformal boost killing vector that preserves the diamond up to this one constant number that scales the vector field. So let's write that down. We're going to need it a lot. And I'm going to scale it so it has unit surface gravity. And it's equal to 1 minus u squared over L squared du plus 1 minus v squared over L squared. And it's also useful to see it in TR coordinates, so I'll do that. And it's just 1 minus r squared over L squared minus t squared over L squared, d by dt. and then minus RT over L d by dr. So this has unit surface gravity. Oh yeah, actually I should explain. Why am I even using the term surface gravity? So the boundary of this diamond is a conformal killing horizon. That means that the killing vector is null on it and it generates it. This the edge of the ball is the bifurcation surface of this killing horizon, conformal killing horizon. And you can define the surface. The concept of surface gravity applies not just to killing horizons, but also to conformal killing horizons. So it's a well-defined concept, and I've normalized this to have unit surface gravity, and that guarantees that the temperature will end up being, as usual, just h bar over 2 pi conjugate to the Hamiltonian that generates this conformal killing flow.
So to normalize the surface gravity, you need some concept of time translation? Or no.
No. It's just...
It's the normalization of the killing.
Yeah. It's the angular normalization at the corner, basically. And the Lie derivative of the metric, this is interesting, with respect to this, let's just take this to be, well, it doesn't matter. This works for any conformally flat space-time. So I'll be doing it in Minkowski space, but actually, one of the possible ways of understanding the cosmological constant I thought might be to actually start with a maximally symmetric de Sitter or anti-de Sitter as just the space I'm perturbing away from. But for the moment, I'll just write this in terms of eta, and then it equals, what does it equal? Minus 2t over L. So that shows indeed it's a conformal killing vector. And notice at t equals 0, it's 0. So the killing equation is actually satisfied exactly on this slice. Okay, now we have this fact that I mentioned earlier, used in this context of this argument, that the state is thermal with respect to the generator of the conformal boost symmetry in the ball. That came actually from an old work in 1982 by Hislop and Longo. I think they specifically talked about a free massless field, but if you look in Hogg's book, and I don't know where you look for a paper that proved it, but for any conformal field theory, basically, if it's a conformal field theory, you can map it by conformal transformation and still have the same vacuum. And so you can map the vacuum in the ball. You can map the whole diamond to the Rindler wedge by a conformal transformation, and then just use the original Unruh effect in the Rindler wedge or the Bisignano-Dickman theorem, to infer that the vacuum inside the diamond will indeed have, where did I write it? Indeed have this form. Yeah, just.
So you're working to first order in the expansion from the point when you say it preserves the diamond. It's not actually the finite diamond.
Ah, right. So here I'm working in flat space. Is that what you're getting to?
Right. When you apply to the curved space-time.
Yeah, I'm not. So it'll turn out, because I'm just considering a first-order perturbation, what I'll be doing is considering a first-order perturbation of the geometry away from flat and of the quantum field away from vacuum, and looking at and requiring that the free energy be stationary with respect to that perturbation. That's why equilibrium was in the title of the talk. So the condition that will end up implying the Einstein equation is that the vacuum is an equilibrium state with respect to joint variations of geometry and quantum field. But because both of those are small variations from the vacuum and the vacuum was flat, when I vary the quantum field, I can treat the geometry as flat.
Does this mean you're only getting the linearized Einstein equation?
No, I'll get the full nonlinear Einstein equation.
By perturbing off of flat space to first order.
Yeah. This is not surprising because, because general relativity is arbitrarily close to linearized around any point. It's a kind of shocking thing when you think about it. No matter how, strong your black hole curvature is and everything, you could just solve the entire Einstein equation everywhere in space-time by solving the linearized equation and then patch together those little linear solutions.
So you're treating gravity classically and having a quantum field on top of that is chosen to be part of a conformal field theory? Is that?
We're going to get to that in a sec. Right. I'll need it to be conformal in some appropriate sense.
I mean, gravity isn't, right? But you're not at the order where that would matter?
Well, the gravity is not, like I said earlier in response to the question about this old derivation, I think the gravity contribution is only appearing in the curvature. So somehow gravity is manifesting as this geometry distortion, but not as one of the quantum fields at the level of this derivation. Because the region is going to be so small compared to any gravitational wavelengths that you don't pick up gravity wave energy on that side of the equation. Yeah?
Sorry. So are you going to get the Einstein equations like in with negative cosmological constant?
I'm not going to get any cosmological constant, except I have ideas about how to get it. So those ideas could allow for positive or negative.
Okay, because in the second argument there, that they use the ADS-CFT correspondence. I mean, you should get, when you get the linearized Einstein equations, they should be like with negative cosmological.
Right, because they're linearizing off ADS.
Okay.
But in my case, I'm not linearizing. I'm getting the full nonlinear equation, although it's, yeah.
So I was just wondering, so are you going to define energy with respect to a Killing vector in the curved space-time?
No, in the flat. That's what I was just saying. Because I'm considering first-order variation of matter and geometry, the correction to the matter variation of entropy due to the curvature of the geometry would be next order. And so I don't have to worry about that. So I'll be calculating the matter entanglement entropy variation on the flat background.
I mean, is that just another way of saying that you would...
We ask questions of what that did, not what it's
going to do.
That's a good idea.
Look, I have a basic question. I'm not sure which category it fits in, but that's,
one will say.
One will say. Okay. In a normal perturbative treatment, we think of fluctuations of the metric field as well. We treat it as any other quantum field. So how are you approaching that and this way of doing this? Are you saying that I'm not allowing it to be a fluctuating field?
I would say my conception of it is that it does those fluctuations to whatever do and contribute, because everything contributes to the value of alpha here. I mean,
so
because
you sort of absorb them all into one.
But you never said how many matter fields you have.
The excitations that you might think of as adding to entanglement entropy in the IR part, which I haven't had a chance to write down yet, would not include gravitons for the reason I keep saying. Okay. So, right. So I just said the key idea, and let's write it in an equation and then try to evaluate it.
So the conformal transformation, which maps your diamond to render space, is it singular on the horizon? The
horizon has to be because it's blowing up a finite region to an infinite one. So that's why I prefer to just discuss everything on the diamond. But yeah, it's a true thing. Okay, so the key idea will be that we consider metric variation and variation of, I'll say, quantum state like that, which is a joint geometry QFT state variation. And then we're going to require, and so since vacuum is being interpreted as equilibrium, we get that the variation of the free energy, and I'm going to have to be specific that it's at fixed volume, like the Helmholtz free energy, equals 0 corresponds to the Einstein equation. Okay. So let's try to evaluate this. I've already said that L should be much smaller than the curvature. I also want it to be much smaller than the localization of any excitation, because I need this variation of the state to be a very small variation in order to justify just perturbing the thermal density matrix, right, to get the entanglement entropy change. So I'm going to also assume L is much less than lambda of excitations. And now this comes the weakest link in the argument, I think. I need to use something from conformal field theory to evaluate disentanglement entropy, because it's only true for a conformal field theory that I know that the vacuum is a thermal state with respect to the conformal boost generator. Now, is any field theory conformal at short distances? This is something I've been asking people. In fact, that's probably what I should have said. I wanted somebody to tell me. Okay, so take the standard model. It has some scales in it. And once we go above, let's say, the Higgs mass, there's a long range all the way up to the Planck scale. Yes?
So there are these exotic theories that string theorists studied which have duality cascades that, as far as I know, just keep flowing. So there are maybe exotic exceptions.
That's good, because if there are, it would be...
But those are infinite n, right? That won't continue forever if n is finite.
Okay.
So this is really a question about this derivation. Clearly, to get anywhere, I have to assume the following. I want to evaluate the free energy. The free energy is going to be something like internal energy minus temperature entropy. The entropy, I'm going to say variation, is going to be a UV part, which is controlled by the thing I just erased, the area term, I'll write it in a second, and an IR part, which just comes from the state variation, not the geometry variation. So this part is going to be alpha delta A, and this part, of course, I want to be able to say that it's given by this formula right here. Namely that it's 1 over t, so delta expectation value, I called it h over there, h zeta over the temperature, which is 2 pi over h bar. So I need to somehow justify that. Yeah.
But let's see, I mean, it wouldn't just be a field theory because there's also gravity, right? You're not going to a boundary representation. You're still saying that you still have the full bulk dimension. So the thing that you need to describe in this diamond will include gravity.
Again, I think not. Not at the level of fluctuating quantum fields, because I took the diamond so small compared to the wavelength of any graviton that's there, and so it can't be assigned.
Why should the wavelength of the gravitons be any different from the wavelengths of the inflatons?
Photons.
Photons. Why should there be a hierarchy?
It's not. They could be the same.
So,
We might expect to have fluctuations on all scales, so you could have gravitational
Look, if I have an
fluctuations
electromagnetic
with the
wave
scale
of a certain wavelength and a gravitational wave of the same wavelength, and now I go in at 1% of the wavelength and I look at the electromagnetic field for that wave, there's an energy density I can measure there. If it's a gravitational wave, there's no energy density I can measure there. So,
but I think if we say that very short distance gravitons will treat as part of matter and appear in the right-hand side of Einstein's equations, and you're dealing with longer distance gravitons that have a wavelength of order L, and anything with wavelength less than L you put in the right-hand side of Einstein's equation.
I don't think that's what I want to do, but it might be, because...
Is your bigger than the Planck scale?
Pardon?
Is it? How big is your diamond?
Oh, yeah, that was one of the other inequalities I had to write down. It is. I want it to be much bigger than the Planck scale.
Right. Okay.
Doesn't that make like QTD
Or the UV scale, whatever that is. Pardon?
Doesn't that make like QCD or the other log flowing gauge couplings a counterexample? Because you need, maybe QCD is asymptotically free in the really, really high energy regime, but if we stay above the Planck scale, it's, approximately conformal, but it's off by an order unity factor.
Well, what quantity is off by an order
The
unity?
beta function of QCD is order unity at, say, 1,000 times the Planck scale, and would presumably enter the argument at that order.
Well, the question is, how does the beta function affect the evaluation of the entanglement entropy of a state that perturbs QCD, which is localized on a scale very, very large compared to the entangling region I'm looking at? So I suspect that what comes in is the ratio of the QCD scale, let's say, let's do it in lengths. The ratio of the size of my diamond to the QCD length scale to some power is probably what comes in.
I bet what it is it's the beta function at the scale of the diamond.
Beta function as a correction to the entanglement? No, impossible. But this has to be determined. If you're right, the whole thing falls flat.
But it is much smaller than 1.
Yeah.
It's right. It's not. It's small, but it's not extremely small. Yeah.
Logarithmically small in the ratio between scales. The coupling.
Log?
I mean, the beta function is the function of the coupling.
Sure.
The coupling is logarithmic.
Yeah, log wouldn't be good enough. This has to be a power of that ratio. What?
He knows.
We're not talking about the beta function. We're talking about the entanglement entropy of a state, which is an excitation of the QCD vacuum, where the length scale associated with that excitation is very long compared to the size of my little diamond. That's the question. Now, how much is that entanglement entropy affected by this beta function being non-zero? I don't know.
So going way back to early work of Mark and so on, I mean, there's this idea that you get geometry from entanglement in boundary theory, and the geometry is building up the geometry of the extra dimension. And your computation here, which, I mean, it seems to be working. I'm just trying to reconcile these things because it's really kind of radically different, because you're assuming all the dimensions. You're not getting any extra dimensions.
Right.
But you're getting the dynamics of, at first they sound like they're the same thing, but then the more you start to think of them, they sound like they're actually almost contradictory, because you're saying that we have all the dimensions there, then we start worrying about entanglement, and that gives us the dynamics of those dimensions. And
right. I'm looking to see if that works that way.
Yeah, but it seems to be working, but
yeah.
How can they, are they the same? Or what? Okay.
I mean, it's not, that's I mean, holography, if it works, is consistent with bulk dynamics up to a point.
You can think perhaps of Mark's derivation as a version where you integrate over this local derivation locally around the horizon and translate some of the quantities to boundary quantities.
But then would that sort of remove quantum entanglement as the fundamental device for generating extra dimensions, right? Because it just gives you the Einstein equation, and you take some, contract some piece of it, and it's consistent with holography, but it's not the foundation of holography. That's what you're saying. The entanglement is consistent with holography, but it's not the foundation of it. Is that?
I was wondering whether this could be interpreted in ADS-CFT, where you thought of putting a cutoff on the boundary theory, and that would correspond to having a finite volume compactification in the bulk, and then you would maybe say, well, that's related to the boundary geometry now being dynamical in some sense.
Yeah, I mean, that would be like you mean like a Reynolds syndrome?
Like a Reynolds syndrome.
Because then you would have this huge and conformal field theory sector, which is coupled to gravity, which is sort of what you're seeming to be talking about. I was also wondering, Juan may shut me up because it's not about what you have said or will say, but it's about what Raphael Busso said. Isn't it true that his covariant entropy bound is about entropy in space-time and geometry of space-time in a similar way? So it's
sure. Okay, let's see what. Okay, I should try to finish quickly, although we had 15 minutes of intros, so 5 more minutes maybe. Let's see. So I totally admit and agree that there's a question of justifying using this formula for a theory that's only an approximately conformal field theory in some sense. I did think about ways we could do better than that, possibly, and one of them is the following. So instead of trying to evaluate the entanglement entropy on this surface using that formula, that's going to be by unitarity the same as the entanglement entropy on this null surface, just because the quantum state evolves from there to there. But on a null surface, it's known that mass parameter, like for example, if you take a massive free scalar field and restrict it to the Rindler horizon, the mass drops out of the quantum field algebra and the quantum state. So this is not a Rindler plane. This has curvature of the cone. So that result certainly doesn't apply directly to it. But it's conceivable that you can justify the use of this formula by integrating over the surface of the cone instead of over this slice. And actually, when you do that, something interesting comes up. So you would get the same result integrating over those two only if the stress tensor is traceless. Because if you take the divergence of the boost energy current, the stress tensor contracted with the boost conformal boost Killing vector, using conservation of the stress tensor, this becomes TAB times CA zeta B, and that's proportional to the metric since it's a conformal Killing vector, so you just get the conformal factor that comes out of that times the trace. So if it's traceless, then it's a divergence-free current, and you'll get the same flux through this surface as through that surface. If it's not quite, well, then you'll get a different result, and maybe you can justify the calculation on this surface for the non-conformal case and not for this one. Actually doing the calculation, I get the following interesting structure, namely the variation of the expectation value. So here I have to put in this current and integrate it over that surface. It equals L to the D omega D minus 2 over D squared minus 1. And then there's a term that is the variation of the T naught naught component. And this would be the whole answer if I just evaluated it on this surface. But it turns out when I evaluate it on this surface, there's an extra term, which is 1 over D times the variation of the trace. And, okay, so I just wanted to put that up because I would refer to it as a possible way to get the cosmological constant in. So, assuming we just have a conformal theory where I don't have to worry about traces, here's my answer for the variation of the conformal boost energy. And you see it's proportional to the variation of the expectation of the stress tensor component. It has some coefficients. I'm supposed to add it to the variation of the area, but I had for the variation of the area this formula, and this formula, and then I should also figure out what U is. And then I'm ready to impose this condition once I fix the volume. So what is U? Okay, the U I claim is 0. Why? How would I talk about the energy inside a diamond in, let's just do something familiar, de Sitter space. So here's a nice conformal diamond, causal diamond in de Sitter space. I want to calculate the total energy because of diffeomorphism invariance. Total energy is a boundary term. It's a boundary term at the horizon, and the variation of it is going to be equal to minus the surface gravity of the cosmological horizon, area variation over 8 pi g. So you don't think of it as an energy, but you think of it as a kind of entropy variation. But this entropy is, as we all know, interpreted in this context exactly as the term I've already written here. So it seems to me that you sort of either include this term in U, or you include this term in S, but you don't do both because that would be counting the same thing twice. So I claim that the right thing to do is say, since I've taken this all the way up to the UV cutoff and I've included all the entanglement entropy, I should set U to 0. Now,
but Ted, if you didn't have gravity in your problem, and you're just minimizing the free energy of your conformal field theory, U minus TS, then you'd know what U was, and you'd know what S was, and of course, it would be true that you should include the delta H term in both places, and they would cancel to give 0. That's how you derive the first law of entanglement or some such thing. So I don't understand.
This thing?
Yeah, that is the statement that you include the delta H term on the matter side in both delta U and delta S.
That's why you get 0.
So I don't. It seems like you're supposed to double count things.
I really don't think so, because you would not. Well, wait a second.
Don, you start by saying there is no if there were no gravity, right?
Yeah, so I'm making an analogy. I'm saying that
right.
I understand why U is identically 0. I would have thought it at least has the matter variation term, and that's the kind of double counting that I seem to say is a bad idea.
Let's think about the first law of black hole mechanics. So we vary the total mass of the space-time, and that's going to be balanced by a variation of the horizon area.
Right.
I could say, well, wait a minute, there's also an entropy associated with that horizon area variation. That's some UV-regulated coefficient times the area variation. And you would say, no, that's already there. That's the variation of the Bekenstein-Hawking entropy. And it comes about as the boundary term in the Noether's identity. So yeah. I'm just saying that you wouldn't count it twice there. So why should I count it twice here?
But are you saying that U is actually identically 0, or are you saying it has no variation?
Well, I'm saying the variation of it should be neglected. I'm not sure if I'm saying
part, or with respect to the matter part as well? With respect to the state of the matter field, or
I guess I'm saying
are both
I'm really saying the net variation. Maybe it has two separate variations that cancel under the matter and geometry part. I don't know. I didn't think about that actually. What the import of it in the end is that I'm going to neglect any variation of it and imposing that variation of F is 0. So I agree it's not solidly justified.
In fact, I guess what Don is saying, if I understand correctly, if you write F as F of gravity plus F of the field theory, and then delta F of the field theory is already 0.
Suppose you could do that, yes. Delta.
Yeah, and then delta F of the field theory.
But that shouldn't be true. It's only delta F of the whole thing that's going to be 0 under this joint variation.
Well, maybe I haven't understood what variation you're making yet. If you're considering all possible first-order variations that vary delta metric and the state, then the variation that leaves G fixed and changes just the state should be 0. When you're saying that you want F to be stationary first order,
right?
Are you making a coordinated change of the geometry in the state?
Yes, because it has to be. He has to use should have to use the equations of motion.
Well, no, but he's saying, yeah, I'm going to derive them. So it should be that I find that you cannot have it be stationary if you only vary. No, I see your point. Hold on a second.
Yeah, the variations are in principle independent.
Right. I guess I am saying it's coordinated. It's impossible to make one without making the other.
But you could.
But it could be that I could do it differently, that I could satisfy the one variation you're talking about of just the state exactly the way you said by this formula. But then when I consider the joint variation, it's being satisfied in a different way because I'm also changing the geometry. your point definitely needs to be considered carefully.
Yeah, maybe we should let Ted finish since it's getting a little late. And,
okay, sorry.
Encourage more dialogue on this offline.
Let me then try to wrap it up. Right, just the last ingredient was the fact that obviously if let's say I varied the metric by just scaling it everywhere. Clearly I'm going to change the area, make it bigger, for instance, and that means I can't possibly have maximized this entropy because this term will just get bigger. But remembering that the free energy should be stationary at fixed volume, I shouldn't allow myself to vary the area freely. I should require that the volume variation is zero. And I can do that, but only if I let the radius of this ball vary. So I have to add to these terms a variation of the volume and area due to the change of the radius, and then demand that the volume variation be zero, and that gives me a variation of the area at fixed volume. Because it's late, I won't write the intermediate steps, but I end up getting that the variation of the area at fixed volume is a little bit different, and it is over 2 d squared minus 1 g naught naught. So if I then use that in this term, so I put this at fixed volume, then I get the Einstein equation. If I assume that alpha has the Bekenstein-Hawking value, then all these numerical coefficients work out to give me precisely the standard normalization of Newton's constant or the Einstein equation. So that's about it. I agree it's got some questionable steps, but I think it's potentially more, it could be potentially be made more sharp than the old argument that I reviewed at the beginning, and it's capturing the same physical ideas underneath it. As far as holography goes, I thought when I was preparing this that maybe I'm like one of those 19th century physicists that tries to explain everything in terms of the ether. Even after like everybody else in the room has realized that holography is the way to go, and I'm still sitting there in the bulk space-time thinking. Anyway, that's it. Thank you.
So if you use this expression, what do you get? If you use this one with the trace of t?
Right, so if you put a cosmological constant and you neglect its contribution to this term, this gives you the cosmological constant term. But I don't see how to justify neglecting its contribution there. The other thing I could say is that we could recently interesting work by Castor, Ray, and Jenny Trashin and a bunch of other people have looked at first law of black hole mechanics, adding a variation of cosmological constant as one of the state parameters. And you can do the same thing here, and that means that you're basically adding a term or subtracting a term, it turns out, that looks like volume times variation of pressure, I guess it is. I don't really know what to call it, but it's conjugate to the volume. And it's possible to just put into this the cosmological constant. So you think of the variation as taking you from one value of the cosmological constant to the other. But I don't I inferred what this has to be to give you the standard Einstein equation with a cosmological constant, but I don't have any theory of what this should have been a priori. So it's a way to get it in there, but...
Wait, this is not a global thing to do to try and change the value of the constant?
Yeah.
So, I mean, how would that fit in your...
You think of it like just a state parameter characterizing the vacuum that you're, the equilibrium state that you're perturbing. That's why I also said earlier it might be possible to get it instead by starting not with a causal diamond in Minkowski, but starting with one in a maximally symmetric different space.
But that would be a different idea than just...
Yeah, that's a different way to do it. And I don't know which one, if any, is correct.
Yeah, the equation that you're going to get here is going to be G nu equals expectation value of T nu, is that right?
Actually, even the variation of the expectation value of T nu. So meaning the difference from the vacuum value.
That's not really the right equation for describing like inflation, right? Because there you want the linearized gravity, and you want to just quantize linearized gravity. And here you have classical gravity coupled to expectation value of the stress.
Right.
Other questions?
Yeah, in terms of what U should be for a little small ball, I mean, there's various proposals for quasi-local mass and general relativity. Yale talked about one this weekend. And they have the property that if your sphere is very small and the matter, and there's non-zero matter, then the leading term is just the energy density of the matter times the volume. But in vacuum, the leading term is the Bell-Robinson tensor times sort of R to the fifth. It comes in at sort of higher order. But it's not zero. So I'm sort of puzzled why U isn't contributing.
If you use that energy, you'd get a different field equation, I guess.
Well, wouldn't that be some leading? That's a sort of curvature
Yeah,
square. Yeah.
right. Be some small correction to the field equation. I mean, another correction is, let's say, what about trace anomaly for, even if you had a conformal fields, you'd have trace anomaly. But that would also be a higher curvature correction to the field equation.
Okay.
Well,
let's thank Ted again.